Okay, welcome back to my kitchen table. And you can see I'm very high tech here with my masking tape. So this is hopefully going to be just as riveting as the last video that I gave you. So if you remember the last time we met in class, we talked about a standard normal curve and how every single standard normal curve, 68% of the population is within one standard deviation of the mean, and 95 is within two standard deviations. So hopefully on last night's homework, which I will have you check if you haven't done so already, on last night's homework you were pretty easily able to answer questions like, what is the probability of a baby weighing between 3.4 and 3.8 kilograms? This is on sheet number 1 from your normal curve packet. And you can estimate that using what's on your chart here, and you can estimate, what's the probability? Oh, there's a 34% chance that if I have a baby, he or she's going to weigh between 3.4 and 3.8 kilograms. And you can read that off the chart. So that's perfectly fine. The problem is when I ask you questions that don't fall exactly one standard deviation or two standard deviations away. For instance, what's the probability of a baby weighing between 3.5 and 3.7 kilograms? It doesn't fall there, so we can't use our estimates. Although I can estimate, and I'm going to say it's going to be something less than 34%. I'm just going to estimate right now that it's going to be, I don't know, like maybe 25%. I don't know. But that's what we're going to be doing now in this video, is using our calculator to get this number. And also we can get this number also off of our calculator. So if you flip over to, I guess it's page 5 in your packets, you can kind of follow along with what I'm doing here. And in this example, I'm going to use a mean shoe size of 9 and a standard deviation of 2. And in general, there are 3 types of questions that I'm going to ask. I'm either going to ask you, find the percentage of the population with a shoe size between two numbers, or I'm going to say, find the percentage of the population with a shoe size greater than a number, or find the percentage of the population with a shoe size less than a number. Those are kind of the 3 varieties. And if I were to put that in shorthand, I'm trying to find the percentage of the population between 9.5 and 11. So that's kind of like the notation that I use. And if I were to draw a standard normal curve for this, so that's 9, what is this? 9, 11, 13. So that's 1, 2, 3 standard deviations to the right, and 1, 2, 3 to the left. So that's 9, 7, 5, 3. So between a 9.5 and 11, it's going to be a number less than 34%. So if I shade it, I'm going to shade it right there. And that's going to be a number less than 34%. I don't know. I'm making up a number. 30%? Something like that. That's just my estimate. And the thing that what I want you to get right now is the fact that there's a lower bound and an upper bound of the shaded region that I have. And the lower bound is 9.5 and the upper bound is 11. In the second example, where it's a shoe size greater than 12.5, I probably should have made more room than this. So I'm just going to do this real quick. This is 9, 11, 13. Oh, I forgot to put the 15 up there. 1, 2, 3 standard deviations. 15. So greater than 11.5. So it's going to be somewhere over there, and it's going to shade all the way over this way, and it never ends because who knows what the biggest shoe size somebody could have. So, 12.5. Whoops. Let me get my eraser out there. All right. Well, I don't have my eraser handy. So that should be a 12.5 there. Boy, this is really bad. Maybe I should go ahead and redraw that. I'm going to redraw that over here. So it's 9, 11, 13, and 15. So greater than a 12.5 would kind of be right about there, and I would shade all the way over. And that number there is 12.5. So in this case, the lower bound is 12.5, and the upper bound is positive infinity, because who knows what the largest size would be. And then here, shoe size less than 6.5, so I do the same thing. There's 9, 1, 2, 3 standard deviations, so that's 7, 0.53. Oh my goodness, I forgot to estimate this one. So this one, that's 0.5 plus 2 plus a little bit from that. I don't know. There's not much there. Maybe it's 4 or 5%. I don't know. That's an estimate. And then less than a 6.5, so that would be somewhere like right around there. And when I shade over this way, my lower bound ends up being negative infinity, and my upper bound ends up being the 6.5, which is right there. Okay, so I just need you to understand this concept of a lower bound and an upper bound for the shaded region, and that there's a negative infinity or a positive infinity in these less than or greater than examples. So now the thing with the calculator is the calculator by default assumes that you're using a standard normal curve, and a standard normal curve has a mean of 0 and a standard deviation of 1. So that's 1, 2, 3, and that's -1, -2, -3. So we need to convert our values into standard values that the calculator can understand. And I'm just going to come back to this example on page 1 for a moment. Do you remember when we calculated all of this here? If I were to put in the standard values for this, this would be 0. This is 1 standard deviation, 2 standard deviations, 3 standard deviations, -1, -2, and -3 standard deviations. So in this case, the standard value for 3.4 is 0 because that is on the mean. The standard value for 3.8 is 1, and the standard value for 4.2 is 2. If I wanted to convert 3.5 to a standard value and 3.7 to a standard value, what I would do is I would use the formula right here. So I'm going to explain how to do that here, and then we'll do these as an example. So, all right, so I have this value of 3.5 that I want to convert to a standard value. Z is the name that we give to the standard value. So I want to convert, I want to find out what the Z value is, or the standard value. So using the formula, Z is equal to X minus X bar over the standard deviation. And right now, 3.5 is my lower bound. 3.5 to 3.7. So 3.5 is my lower bound. So I'm just going to put a Z for the lower bound. And this is going to be the X for the lower bound. So the X for the lower bound is 3.5 minus the mean, and in this case the mean was 3.4, divided by the standard deviation, and the standard deviation in this case was 0.4. So if I just pull up my calculator, this is 0.1 over 0.4, which is 0.25. So this value right here, the Z value is 0.25, which kind of makes sense. It should be between, 0.25. It should be between 0 and 1. And if I do the same thing, I find the Z for the upper, that's equal to the X of the upper bound minus the mean divided by the standard deviation. So that's 3.8 minus 3.4 divided by 0.4. Oops. Did I do that right? Oh, sorry, that's 3.7. I should be using 3.7 minus 3.4 divided by 0.4, which is 0.3 divided by 0.4, which ends up being 0.75. So my gut check says that these are right because the numbers, the standard values, should be between 0 and 1 for 3.5 and 3.7. So those are the standard values. Let's do the same thing over here. So for the examples that I have above here, I need to find the Z values for all of my lower and upper bounds. So I'm going to find the Z values for 9.5 and 11 for this example. I'm going to find the Z value for 12.5, and I'm going to find the Z value for 6.5. So you could pause and try this on your own, or you could follow me as I do it. So the Z value is equal to 9.5 minus 9 divided by 2. And I can pick up my calculator, and I do that, so that's 0.5 divided by 2. And if I do that on my calculator, that equals to 0.25. Okay, so now I'm just going to do it again. The Z value for 11, That's 11 minus 9 divided by 2. That's equal to 2 divided by 2, which is 1. Oh, that makes sense, because look, 11 is 1 standard deviation away from the mean. So that's good that that was a 1. That kind of just confirms my calculation before. So the z-value for 12.5, that's 12.5 minus 9 divided by 2. And that ends up being 3.5 divided by 2. And if you do that on your calculator, that's 1.75. And finally, the z-value for 6.5, that's equal to 6.5 minus 9 divided by handy dandy 2, which happens to be our standard deviation here. So this ends up being negative, what is that, 2.5 over 2, which divided by 2, negative 1.25. I probably should have done that in my head. So that makes sense, because 6.5 is below the mean, and if I put in my standard value 0, 1, 2, 3, negative 1.25 is between negative 1 and negative 2. So that's good. So these are all of my z-values. And tomorrow, or the next time we meet in class, we are going to be using these z-values for some other things besides the standard normal curve. You can use it to compare two numbers. So now we're going to plug it into the calculator. I'll do it on the TI-83 and 84 first. So, so on the 83 and 84, there's this second, above ours it says distribution. So if you hit that and you do a normal CDF, that stands for normal cumulative distribution function. So we select that, and you're just going to type in the two z-values. So here, the z-values that we calculated were 0.25 for the lower bound, and then 1 for the upper bound. So I'm going to do 0.25, and then a comma. Where is the comma? Oh, there it is, comma, and then a 1. And it gives me back 0.2426. So that's the probability. So I'm going to multiply that by 100. So we could say that this is 24.3%. That's the number back from the calculator. We had estimated it as 30, so that's a good number there. So let's do this one now. So here, what is this? Oh, so this is from 12.5 to infinity. So when it's 12.5 to infinity, then I'm going to use this 12.5, so that's my z-value of 1.75, and that is infinity. But the way infinity is represented on the TI-83 and 84 is for positive infinity, it's E99. For negative infinity, it's negative E99. So I'm going to type in distribution, normal cumulative distribution function, 1.75, comma. Now I'll do the positive infinity. Where's that funky? Oh, that's the weird E right there. That's right above the comma. So second E99. And I multiply that by 100, and lo and behold, it says it's 4%. Oh, look, I said it was between 4 and 5%. So that, coming back from the calculator, is 4%. And then for this example here, I again do a normal cumulative distribution function. This case I want negative infinity, so negative E99, and my upper bound 6.5, which is negative 1.25. So I again do negative where was that? E99, comma, negative 1.25, and lo and behold, I get, multiply that by 100, so that's 10.6% of the population, which I had estimated, oh, I didn't estimate, but it would have, that estimate sounds about right. If I got a number back like 15 or 50% or something, I know that it would be incorrect. And just to kind of show you that this really does work, if you do a normal cumulative distribution function from 0 to 1 standard deviation away, lo and behold, that ends up being 34%. I can't believe my phone is ringing right now. was my mother calling. She's going to call back, I know. Okay. So, all right, well, that was awkward. All right, so that's 34% of the population. That's one standard deviation away from 0 to 1, which makes sense. That's the same thing that we kind of came up with right there, from 0 to 1. That's 34%. That's the same 34%. Let's do the same thing on the Inspire. So on the Inspire, if you go to a calculator window and hit Menu and go to Statistics and go to Distributions. So Statistics, Distributions, and then you see a normal CDF there. So when you do that, you can see that the lower bound, it automatically populates in negative infinity right there. So that's what negative infinity looks like on this calculator. And the E on my keyboard, it looks like this. It's like the funny looking double E, E, E. That's the E that you would use. And make sure for the negative sign, you're using this negative sign. Don't use this negative sign over here. So I'm going to do the same thing. My lower bound in this case is 0.25, and my upper bound is going to be 1. Oops, my lower bound was 0.25. And is that? And my upper bound is going to be 1, and I tab over to OK, and I end up getting 0.24, multiply that by 100. So that's the same 24.3% that I had before. And Menu, Statistics, Distribution. So in this example, I'm doing the normal cumulative distribution function again. In this case, I'm going from 1.75 to positive infinity. So 1.75. Why am I having 1.75? Now I go to positive infinity, so I'm going to type in 9, the funny E, 999. That's the way that it represents it. And I hit OK, and it gives me back the same number, the 4% that I had before. And then I do Menu again, Distributions, Statistics, Distributions, and I do a cumulative distribution, normal cumulative distribution function. And in this case, I'm going to go, the lower bound is negative infinity and the upper bound is negative 1.25. So I'll keep that there and put in negative 1.25. And, oops, what did I do? Oops. And it gives me back the 10.6% that I got on the TI 83 and 84. So that's how you do that. I want to show you kind of the reverse lookup, and then I can continue and do some examples, but you don't have to watch me while I do the examples if you don't need any more help. So I'm going to move over to page 6. So in this case now, we're going to do percentiles. And if you've, you should probably actually at this point stop, and you should probably try a couple problems on page 7. I think that would be the best thing for you to do. So I'm going to go ahead and do a sample on page 7. You can finish problems 1, 2, 3, 4 on page 7, and you can pause me if you need to. So in this case, I'm going to draw the standard normal curve. The mean is 100 and the standard deviation is 15, so that's 115, 130, 145, 1, 2, 3. That's 85, 70, and what is that, 55. Find the probability of randomly picking an IQ higher than 125. So it's going to be something like that. So I'm going to estimate that that's around, I don't know, 5% estimate. But my estimate is not good enough. I have to do it on my calculator. So what I'm going to do is, in this case, my lower bound is 125, and my upper bound is positive infinity, because this keeps going. And I'm going to convert this 125 to a z-score. So my z for my lower bound is equal to 125 minus 100 over 15. So that z for the lower bound ends up being, what is that, 25 divided by 15, which is 1.6 repeating. Decimal places do make a big difference here. And for the upper bound, it's going to be positive infinity. So my z for my upper is whatever it is on your calculator, 9E999. So now on my calculator, I'm going to do a normal cumulative distribution function from 1.6 to positive infinity, whatever that is on your calculator. And when you do that, I always lose that E, 99. I guess I should show you that. That's 1.6 repeating, comma, E99. And that ends up being 4.78%, or I'm going to round this to 4.8%. Okay, which was very close to my estimate that I had before. So continue the rest of these. When you're done with numbers 1, 3, and 4, you can start the video again. So now, now I'm going to do percentiles. And you've probably heard of percentiles, and most people don't understand what percentiles are. So when people give you information in percentiles, in effect what they're saying, and I'll just use this example. In effect, what they're saying is they're saying that you are better than a certain percentage of the population. So if you score if you score in the 75th percentile, you have scored better than 75% of people. If you score in the 50th percentile, you're right at the mean and you score better than 50% of the people. If you score in the 99th percentile, you score higher than 99% of the people. And I'll tell you, when my children right now, their height and weight is in the 95th percentile. So it's, they're big boys. Okay, so in this case, again, we're going to have a mean shoe size of 9 and a standard deviation of 2. And there's two types of questions that I'll ask. So I'll tell you, if my shoe size is a 10, what's my percentile? Or I'll ask, if I'm in the 90th percentile, what is my shoe size? This question right here is exactly like what we did right now. Because in effect, what I'm saying is, if my shoe size is 10, what percentage of the population is higher, is my shoe size bigger than? And if the mean is a 9 and the standard deviation is 2, so that's 11, 13, 15, 7, 5, 3. My shoe size is a 10. What percent of the population is my shoe size bigger than? Well, it's the same exact thing that we did before. Oops, stop right there. So in this case, I'm going to do a normal cumulative distribution function from negative infinity, and then I'm going to go to the z-value for a 10. The z-value for a 10 is 1/2, so that's 0.5. So that's the same thing that we just did. So if I'm asking for a percentile, in effect, I'm just asking what percentage of the population has a score less than that, and it's always negative infinity on the lower bound. So that's what that one is. The reverse of this is, if I'm in the 90th percentile, what is my shoe size? So now I'm giving you the percentage and I want the shoe size back. And this is the one where it's kind of the reverse lookup. So in this case, if I'm in the 90th percentile, 9, 11, 13, 15. So if I estimate this is 50% of the population here, this is another 34%. So the 84th percentile, if you have a shoe size of 11, you're in the 84th percentile. If you have a shoe size of 13, you're in the 97th percentile. So you're going to have a shoe size between 11 and 13 if you were to estimate it. So, so we can use our calculator to get the exact value. So instead of using inverse norm, this is the reverse. I'm putting in the percentage and I'm going to get out the z-value. So in this case, what I'm going to do is I'm going to do what's called an inverse norm. And I'm going to take this 90th percentile, and that's 90 over 100. I'm going to do an inverse norm of 90 over 100. And when I do an inverse norm of 90 over 100 on my TI 83 and 84, I go back to distribution, I go to inverse norm, and I do 90 divided by 100. And that gives me back the z value of 1.28. I'm going to do that on the Inspire also. So here, if I go to Menu, Statistics, Distributions, Inverse Normal, I'm going to put in the percent of the population, that's 0.9, or I could just type in 90 over 100 if you want to do that. 90 divided by 100, you could do that too. And if I tab over to OK, it ends up giving me 1.28. So in both cases, it gives me the z value of 1.28, which makes sense. So this has a z value of 0, 11 has a z value of 1. I said it was someplace in between 11 and 13, so it's somewhere right around there. So, and that's the z value of 2. So the z value is 1.28. So I'm going to use the same formula that I used before, except now I've got the z value of 1.28, and that's equal to whatever the value is minus the mean. The mean in this case was 9, divided by the standard deviation. So it's the same exact formula we used before. Now we're just solving for x instead of solving for z. So if I multiply both sides by 2, I get 2.156 is equal to x minus 9. I add 9 to both sides, and I get x is equal to 11.56. So if I'm in the 90th percentile, what is my shoe size? My shoe size is about 11.5. And that's how to do percentiles, either getting the percentile or finding the score given a percentile. So you can do as many problems of this. You do lots of problems like this. So now I would go back over here to page 7, and it says the scores on a standardized test are normally distributed with a mean of 50, and a standard deviation of 10. So that's 50, 60, 70, 80, 50, 40, 30, 20. So if I want to find the 80th percent